Hi there, Mr. Sutton here with the BC Calculus 7-6 Extra Practice Number 1 solutions on Lagrange error form. For this no calculator free response, we're given this function f, which is defined for all derivatives and has this crazy piecewise kind of setup here. And they're also giving us this function g, which is just 1 plus the integral of f from 0 to x. So for this first part, they want us to write the first three non-zero terms in general term for a Taylor series for cosine, and then do some other stuff. Well, let's start with cosine. So that's going to start as cosine of x equals 1, and then we're going to do, it always goes plus minus with sine and cosine. So cosine we've got minus, and then we do all the even powers now. So we're going to have x squared over 2 factorial plus x to the 4th over 4 factorial. And then they also wanted the general term, so we could write minus x to the 6th over 6 factorial, but they only asked for the first three non-zeros and the general. So the next one's going to be, we're going to have a negative 1 to the n power, and then we're going to have x to the 2n, because we're going by 2's every time, and then 2n in a parentheses with a factorial in the denominator. All right, so that was the first thing they wanted. We get a point for that. Then they want us to use that series to write the first three non-zero terms in general term for the f function itself. Well, the f function itself involves this cosine of x minus 1 over x squared piece. So let's figure out what that comes out to. If I subtract 1 from cosine of x, that's going to be all of this stuff, but without the 1 in the beginning, because we just subtracted it. So we're going to start with negative x squared over 2 factorial and go from there. Next, to get the f function itself, we have to divide all of these now by x squared. And if you're wondering, well, what about this? It's not equal to 0, so what about that piece of it? What about the constant in the beginning? Well, f of 0 is negative 1/2. So we should end up with a negative 1/2 in the beginning when all is said and done. But let's go ahead and just divide all of these by x squared and see if things take care of themselves. So dividing by x squared, we have x squared over x squared is just going to be 1/2 with a negative out in front. So that actually does take care of itself. And for this next one now, we're going to have, let's see, this is going to be x squared over 4 factorial. And then we need one more term. We would have had minus x to the 6th over 6 factorial. So subtracting 2 from the exponent, because we're dividing by x squared, that's now going to be minus x to the 4th over 6 factorial. And for our general term, just dividing this by x squared, we have negative 1 to the n, and then this is going to be x to the 2n minus 2 over 2n factorial. And there's other ways of writing this, but we're going to stick with this and call it a day on this part. On this problem, we want to use our Taylor series that we found in part A to figure out if f has a relative max-min or neither. Now, the key on this one is realizing that your series gives you perfect information about the original function at f of 0, f prime of 0, f double prime of 0. It's pretty much everything you need to do your second derivative test. So let's go ahead and rewrite the series from part A. Here's what we had before. And based off this series, we need to figure out f prime and f double prime. Since I don't have a linear term in here, that means that my f prime of 0 derivative must itself be 0, because we zeroed out the x that should have been there. Now we need to figure out f double prime of 0. But note that since f prime of 0 is 0, we at least have a critical value and have to keep going with the problem. So in general, the coefficient of x squared ought to be f double prime of 0 over 2 factorial. Now the actual coefficient of x squared in this series is 1 over 4 factorial. So to get f double prime of 0 by itself, I need to multiply both sides by 2 factorial. 2 factorial over 4 factorial, that's really 2 over 24, which is 1/12. The important piece of this, though, is that this is a positive number. Since my first derivative is 0 and my second derivative is positive, well, that means that I'm at the turnaround spot on a function that is concave up, which means I must be at a minimum. So I can conclude, therefore, that f has a relative minimum at x equals 0 by the second derivative test. For this problem, we want the 5th degree Taylor polynomial for g about x equals 0. So in order to do this, I need to do 1 plus the integral of f from 0 to x. And since I want a 5th degree polynomial when all is said and done, that means I need up to the 4th degree inside this integral. So I'm going to start by giving this function a name, actually, because I'm just doing a polynomial, not the full g function here. So I'm going to call g of x approximately equal to p sub 5. So this is our 5th degree g polynomial. All right. So this is going to be 1 plus the integral from 0 to x of, and now I'm just going to put the first 3 terms of my f series in here. I only need up to t to the 4th over 6 factorial because, again, I just want 5th degree after I get through this process. Now, to save myself a little time, I notice that when I take the antiderivative of all of this in terms of t, I'm going to end up with t's in every term, which are all going to zero out when I plug 0 in as the back half of my fundamental theorem. So rather than waste all that time, I'm just going to take the antiderivatives and plug x in immediately and know that I'm subtracting 0 after I do that. So I end up with 1, and then we're going to have minus 1/2 x, or x over 2, plus this will be, let's see, x cubed over 3 times 4 factorial. I'm not going to bother simplifying until I absolutely need to. Next we have minus x to the 5th over 5 6 factorial. And that gives us our 5th degree here, so we're all done with this problem. For this last part, they're telling us that the Taylor series for g about x equals 0 evaluated at 1 is an alternating series with individual terms that decrease in absolute value to 0. I think I've seen this wording before. We want to use the 3rd degree Taylor polynomial for g about 0 to estimate g of 1 and then explain why this estimate differs from the actual value by less than 1 over 6 factorial. Okay, so let's start with the estimation part. We need a 3rd degree Taylor polynomial for g that we need to use to estimate g of 1. So let me start with what I had on part C. This was my 5th degree polynomial for g. Well, my 3rd degree polynomial is just going to be all of this, but we're chopping off this last term. So when I do g of x now, g of 1, that's approximately equal to p sub 3 of 1, a 3rd degree polynomial version of this. And that's going to be, let's see, 1 minus 1 over 2 plus 1 cubed over 3 times 4 factorial. So basically just taking the first 3 terms, the cubic up to the cubic term, and plugging in 1 for x. Now we could leave it like it is, or we could actually simplify it. So let's see here. This is really 1 over, let's see, 3 times 4 factorial. That's 3 times 24, which is 72. So we have 72 over 72 minus 36 over 72, getting a common denominator here. That leaves me with 36 over 72 plus 1 over 72, which comes out to 37 over 72. So there's our estimate, which we needlessly simplified. Next, we want to explain why this estimate differs from the value of the true value of g of 1 by less than 1 over 6 factorial. Well, they didn't come out and spell it for us in so many words, but they noted here that this series is an alternating series with individual terms that decrease in absolute value to 0. Basically, they want us to use the alternating series error bound here. So that error bound states that if your terms alternate and decrease in absolute value to 0, then your error is less than the absolute value of the next term. So basically, we can just say error is less than the absolute value of whatever the next term of this series is with 1 plugged into it. Well, that's just going to be error less than absolute value of 1 to the 5th over 5 times 6 factorial, which, I mean, simplifying 6 factorial is kind of a pain, but the good news is we don't have to. They just wanted us to show that our error was less than 1 over 6 factorial. Well, if we have 1 over 5 times 6 factorial, that's definitely going to have to be less than 1 over 6 factorial because your denominator is larger by multiplying it by 5. So I'm just going to write less than 1 over 6 factorial, and then I'm actually done, and I've proven what they told me to set out to prove. For this no calculator free response problem, they're telling us f and g are functions given by, let's see, x e to the x cubed, and g is the integral of f. And then the graph of the 5th derivative of f is given down below. So first task, based on all this information, we want the first 4 non-zero terms in general term of e to the x, and then they want us to write all of that for f of x. All right, let's start with e to the x because we kind of need that since f is built out of e to the x. So e to the x, first term is going to be 1, and then it's going to be plus x squared over 2 factorial, plus x to the third over 3 factorial, and this pattern continues all the way up to x to the n over n factorial. So we've met the first condition they said. They just wanted first 4 non-zero terms in general term for that. But now we need to write out a function, a series for f of x. So let's do this one transformation at a time. I'm going to start by writing out the series for e to the x cubed. So to get that, I just have to plug x cubed in for all the x's in this series. And I'm going to go ahead and simplify as I go here because it'll help me for some problems down the line. So my first term is going to be 1. And then I have x with x cubed plugged in, which is just x cubed. This is going to be x cubed squared, which is x to the 3 times 2, x to the 6th over 2 factorial. Here we've got x to the 3 times 3, so that's x to the 9th over 3 factorial. And all the way out here, this is going to be x to the 3n over n factorial. All right, we're almost there. To write f of x, we now need to stick an x out in front of all this. So this is the function x times e to the x cubed now that we're writing a series for. So multiplying everything by x, this first term just becomes x because 1 times x is x. Then we have x to the, let's see, add the exponents, x to the 4th. This will be x to the 7th over 2 factorial, x to the 10th over 3 factorial, and all the way out here, our general term, we're going to have x to the 3n plus 1 over n factorial. For this problem part, we want the first 4 non-zero terms of our Taylor series for g. Now remember, g is just the integral of f from 0 to x. So let me just write out my f function that I got from part A. So there it is again. Now I'm actually just going to take the integral of this. They said they want the first 4 non-zero terms, so we're just going to take the antiderivative of each one of these. Now when I do this, I'm going to get expressions that all have x's in them, so that when I plug in this bottom limit of integration, that would end up canceling all of those out anyway. So I'm not going to bother putting this in an evaluation box with the t and a 0 to x. We're just going to go straight to our antiderivative with the x's in it. This first one bumps up to a power of 2, and we divide by that, so 1/2 x squared. And then this one goes up to 5th power, dividing by 5, we have x to the 5th over 5. Then this will be x to the 8th over 8 times 2 factorial, which is 16. And finally, we'll have x to the 11th over, this is going to be 11 times 6 if I feel like simplifying it, so 66 down there. And there we are. For this part of the problem, they want the 5th derivative of g at 0. So the key here, and this is from part B now, you've already written out a series for g. Now this series, since it was based off of f, which was based off of 0, Maclaurin series at 0, this gives us perfect information about the g function at x equals 0. We have all the derivatives we could want plus the function value. So now in general, the derivative of x to the 5th of a function is going to be the 5th derivative of 0 over 5 factorial. And this is in the g function specifically, so it's the 5th derivative of g at 0. But now this coefficient in this series is actually 1 over 5. So if I want the 5th derivative, I just need to multiply both sides of this equation by 5 factorial. So I've got 5 factorial over 5. 5 factorial is really just 5 times 4 factorial. So the 5's cancel, leaving me with just a 4 factorial up top, which I could reduce and simplify if I wanted to 24. For this problem, we're given this 5th degree Taylor polynomial for g about 0. We want to use Lagrange Error Bound to find an upper bound on absolute difference between this polynomial and g of 1/2. So basically they want error using Lagrange. So let's set up our error bound for Lagrange. That's going to be error less than or equal to big fraction. And now in the numerator, we need the max derivative of this function. And let's see here. So that means we need an interval. Our interval always goes from the center to the input value. We have a center of 0. We're trying to input a value of x equals 1/2. So I want max derivative from 0 to 1/2. Which derivative do I want? Well, if I'm using a 5th degree polynomial, that means I want the 6th derivative. And be careful here. We want the 6th derivative of the g function, not the f function, because this is a polynomial approximation of g. So I'm writing a g derivative 6, 6th derivative of x. And now if this is a 6, everything else in here is going to be a 6. We're going to have a 6 factorial. This is going to be x to the 6th power out here. So now we have to figure out how to maximize this 6th derivative of g. Well, the key on this one, since they didn't really give you any information about the derivatives of g, you have to go back to the f function. The link here, and if you look up here, this formula is the real crucial link. If we take the derivative of these, if we start taking derivatives of g, and this is our only source of information on g really, we see that g prime of x equals, using my FTC, f of x. Well, if g prime of x equals f of x, that means g double prime of x equals f single prime of x, and g triple prime of x equals f double prime of x. You see where I'm going with this. The derivative on g is always one more than the derivative on f. So that means if we want to write absolute value of 6th derivative of x, that's the same as absolute value of the 5th derivative of f. Well, what is the 5th derivative of f? It's all the stuff in this graph here, and this is what we're trying to maximize now. So what's the highest that the 5th derivative of f, aka 6th derivative of g, gets on this graph? Depends on your interval. Looking at my interval here, I want to maximize on the interval from 0 to 1/2. So I'm only going to consider this right half of the graph here between 0 and 0.5. And looking at these values, the highest I can get is up here at the very end at 500. So this is going to be less than or equal to 500. Okay, well, time to plug a few things in. This whole max numerator is just 500. 6 factorial can stay where it is. X to the 6, we're really plugging in 1/2, so that's 1 over 2 to the 6. And this ends up being our upper bound, our error bound. Now, there was nothing else we needed to use this for. This is an upper bound, so we've actually finished the problem.